A lot of research has been done on the aerodynamics of cars, particularly single cars with head-on wins. But what about when one car overtakes another? In fact, for most of us, it is much more common to be driving around with other cars around than not. So how does having another car around your car affect its aerodynamics? That is what we're looking at today. How does overtaking another car affect the lift, drag, and even side force of your car? To answer this question, we are looking at this paper called Computational Analysis of the Fluid Structure Interaction Occurring in a Model of Two Vehicles Overtaking Each Other. It is open access, so you can find it in the link below. So in addition to looking at the lift, drag, and side forces, these researchers also looked at the forces trying to deform the surfaces of the car, because if you apply a suction force, then that is going to suck out a panel on your car, and vice versa for a pressure force. So they're not only looking at the fluid side of things, but also the fluid structure interactions, which is very complex. And to do that, they looked at two armored bodies, which may not seem very car-like, but in fact, as shown here in figure 1, they have all the general components of a car, and these armored bodies were actually developed like a long time ago, maybe 40 years ago or so, to replicate all the other major flow physics of a car, but without the added computational costs. So we get the major flow physics components, but not all the minor things like, for example, a mirror or a door handle, things like that. And compared to some cars, this armored body is actually more aerodynamic, believe it or not. So to investigate this overtaking maneuver, the researchers used CFD, which affords a lot of flexibility and the ability to actually perform the overtaking. And I mean, trying to do this in a wind tunnel is nearly impossible with full-scale cars, and that is for a few good reasons. One being that you need a really big wind tunnel, probably one bigger than anything currently used. Another major difficulty is the wind tunnel mechanism that would move the cars relative to each other. And a third major difficulty would be the system that would then measure the forces. So perhaps the best way to overcome these latter two difficulties would be to use stings and to hold the cars in place, probably from overhead, and then move them around on a moving floor, so a belt. But then you still have a major problem with the size of the wind tunnel. You couldn't use full-scale cars. Now with this CFD, they didn't exactly overcome the size difficulty because these armored bodies aren't full-size cars. They measure 74 centimeters long by 27 centimeters wide and 20 centimeters high, so about 1 to 7 models. And they don't give the exact reason why they chose a scale model, and also why about 1 to 7 in the ratio, but I imagine it has to do with their validation data, which we'll get to in a little bit, and also potentially conserving the number of cells they need. As we'll also see later on, they have made very large refinement regions to accommodate this overtaking maneuver, and we'll go through why that is. So based on these dimensions and the velocity of 30.3 meters per second, which is 110 k's per hour, the Reynolds number of at least the car being overtaken was 390,000. So that places it towards the fully turbulent regime. I'm a little hesitant to say that it is fully turbulent because while this probably is, the armored body is very smooth to begin with. So there isn't a lot of things there to trip the boundary layer into turbulence. Now that's for the car being overtaken. For the overtaking car, they don't seem to say exactly what the velocity of that car was. I can't find any exact number, but based on the approximate time it took for the overtaking car to go from its starting position in figure 2, so figure 2 is down here, to side by side being overtaken, which is about 0.5 seconds, I would say that the overtaking car is traveling at about 36 meters per second, which is about 130 kilometers per hour, so pretty fast. And that's almost about as fast as what you would test a car regularly in a wind tunnel for the WLTP standards. So one thing that is interesting is that they set the ground condition to be a no-slip condition, which isn't what you are supposed to do. So that is because when you are driving along, the air isn't actually moving over the ground, at least not globally. So okay, around the car might be inducing some flow that then hits the ground, but then when you say that you're traveling at 30 meters per second, what that means is that the ground is stationary and the air over the ground is also stationary compared to the ground, but then you're moving through the air and over the ground at 30 meters per second, not the other way around. So the air and ground stay relative to each other at 0 meters per second. So as such, the 30 meter per second velocity doesn't actually exist for the air, and hence there's no boundary layer forming over the ground. The way they've prescribed this boundary condition means that from the very inlet, really, a boundary layer will start to form. And if you want to study an actual car and get accurate results, then that is a problem because by the time the flow reaches the car, the boundary layer can easily be a few centimeters tall, and that changes the flow physics of the car. Here, while it is a bit problematic, it is still largely okay because we're looking just at the general objects and not a specific car. So this is a no-slip condition is kind of excusable for this specific case, but it wouldn't be if, let's say, you were testing an actual car that an automotive manufacturer was going to be building and selling. So the terminus model that they used was the SST Amiga, which is good, and the authors take full advantage of it because they have an average Y plus of 75, which this terminus model can handle. Now we can see their surface and volume meshes around the cars in figure 4, if I scroll down to figure 4 here, and we can see the inflation layers over the ground in the bottom figure here. So zooming here and in here. We can also see their inflation layers over the car, but it seems like they are only using about 2 or 3 layers, which I don't think are enough. But then again, the Y plus values are very big, so maybe the boundary layer is about this size too. I'm not too sure, they didn't go into that. So in the top part of this figure 4, we see the mesh around the armored body, and there are some really good refinement regions. They did a good job around the front of the body too, which makes a lot of sense to put in a lot of refinement here. And that's because if you just had a sole like car in CFD, you wouldn't need as many cells. But because we have an overtaking car, you have flow hitting the downstream car from the upstream one. So it is no longer well behaved, this flow hitting the downstream car. And as such, you're going to get a lot more terminal structures hitting the trailing car, and you want to resolve them in order to then be able to accurately model what is happening over the rest of the car. Hence why you have this refinement region in this upstream region. That's quite good. Now, the researchers say that they used 17 million cells for their CFD, which when you look at figure 4, it doesn't seem like 17 million across the board. I mean, sure, the refinement is very good, but not 17 million cells worth between the two cars. But when you look at figure 5, you then get a much better appreciation as to how and why they used so many. And these figures show very concisely the difficulty in CFDing overtaking maneuvers. So they have 2 armored bodies here, 1, 2, and each one has its own refinement region. But then going through the entire domain is this big strip of very refined cells. And this strip alone would be like 10 million cells or so. And they need this very large refinement region for a couple of very important reasons. The first is that you need to refine the flow coming off of one car that then hits the other car, because the way the wake of the upstream car evolves, as we've covered, has very important consequences for the downstream car. But the second reason why you need to have such a large refinement region here going straight through the entire domain is because I believe the authors here are using an overset mesh. Now, they don't seem to say explicitly that their setup is an overset mesh, but from this setup, what I can see, it seems to be an overset mesh. So an overset mesh is where you have your general mesh in your domain, but then you have your object in its own like local mesh, and your object's mesh is actually separate to the domain's mesh, and it can move relative to the domain's mesh. That way, like here for example, you can change the location of your object in the domain relative to anything else. That is how they're getting their overtaking car to move through the domain and change its relative position to the upstream car. Now this is a really cool and sophisticated CFD method, and if you want to learn how to do this and in OpenFOAM, which is a completely free and really good CFD software, check out our links below where we teach you how to do exactly this. And you might be thinking, okay, so you need a refinement region here, but why does it need to be so refined? I mean, from this view, it seems like the refinement of the central strip is just as fine as the armored bodies themselves. Isn't that excessive? Well, for overset meshes, it isn't, and this level of refinement is still needed, and that is because when you think about what is happening in the overset mesh, you have the global flow, and then the information in the global domain is then copied to the cars mesh. What happens in the cars mesh is copied then back to the global domain so that the flow can evolve and go on its merry way and go downstream. So if you have your cars mesh as very fine and the mesh of the global domain around the car as much coarser, you now don't get a good representation of what is happening because you only have coarse information being shared with the overset mesh around the car, and that is going to make the flow physics around the car more erroneous. All the finer features that you have happening in the local mesh aren't going to then be put into the global domain because the cells aren't refined enough, they're too coarse, and you lose that information as well. As such, you need to have similarly refined meshes in the global mesh around the car to the overset mesh around the car. Otherwise, too much information is lost. And you can see here, they've kind of done that for probably the inside 3/4 of the car. The outside part, they do have a less refined mesh in the global domain, and that's because, again, the wake from that isn't that important because it's not hitting the downstream car. So they had to balance quite a few things going on here. So the overset meshes are very powerful and allow you to do some really cool things, but you have to do it right, otherwise you'll get wrong results, and it's very likely that the CFD will actually diverge as well. So that's quite an interesting point that you need to make these meshes very fine to get the CFD to converge. Now, these researchers unfortunately didn't do a mesh-independent study, which, given the number of cells they used and the fact that they are using an overset mesh, it is understandable. They maybe just didn't have the resources for them. But they did do a validation study, which is a little surprising given how hard it is to do this experimentally, but I guess this is why they used the scale models. And maybe also why they used the no-slip boundary condition. Perhaps the wind tunnel and experiments setup, which was done 20 years ago, didn't have a moving ground capable of doing this maneuver. So in figure 7, we see the comparison between the experimental results in blue and the CFD in red. So we see this the side force coefficient, then the drag coefficient and the yawing moment coefficient. And these are the forces on the car that is being overtaken. Overall, I'm really impressed with how well the CFD matches the wind tunnel results. The side force coefficient is almost bang on, with just a fairly minor difference at the peak side force and when the side force recovers and the car is finished overtaking. Apart from that, they're very, very close. For the drag coefficient, it is a little less accurate with a consistent underprediction throughout the maneuver. The general trend is very well replicated, but the only point where the drag coefficient is very close to the experiments is from X on L position of 0 to about 1. So literally when the overtaking car is side by side to the car being overtaken, and then the overtaking car zooms ahead by 1 car length. Now for the yawing moment coefficient, shown in this bottom figure here, it is really good and quite close to the experimental data again. So similar to the side force coefficient, it is really only at the peak side force where the CFD substantially deviates from the experiments. So I think the CFD is pretty good with all things considered. It is a hard setup and there are some things that the researchers did to make it easier, like using armored bodies, but then there are also some very complex CFD methods going on too. So overall, I'll rate this CFD probably about a 7 out of 10, and we can trust the general trends and flow viz. The exact forces perhaps are a little bit off, but I don't think it matters too much here because we are seeing changes in the forces well over 5 or 10%, which is what this CFD might be accurate to. So I think the force coefficients can largely be trusted here given the context. Now, from this figure, we can also see how the forces on the car being overtaken change throughout the overtaking maneuver. So the x-axis is normalized, the normalized distance, so x on L, which tells us how far upstream or downstream the overtaking car is, with respect to the car's length. In other words, car lengths upstream or downstream. So 5 car lengths downstream, 5 car lengths upstream. Looking at the drag coefficient first, so this middle figure, we see that the car being overtaken, let me zoom in a bit actually, here we go. So the car being overtaken doesn't see much of a change in the drag coefficient until the overtaking car is about 1.5 car lengths about downstream of it, so about here. So when the overtaking car is a few car lengths downstream, the car being overtaken isn't really affected in the drag coefficient at all. It's probably within error really. Then as the overtaking car gets to within 1 car length downstream, the car being overtaken experiences a huge increase in its drag coefficient of up to 150 counts. And as quickly as it skyrockets when the 2 cars are side by side, it then drops even more, and the overtaking car has pulled ahead by almost a car length. The car being overtaken experiences a massive drop in the drag coefficient of about 100 counts. So within like 1.5 car lengths, the drag coefficient of the overtaken car drops by 250 counts. That's a huge amount. So I don't know what the drag coefficient of this car is, but I suspect it's about 0.275 or so, which is about typical for an armored body. So a 100 count reduction here or a 250 count change is huge. And even when the overtaking car zooms ahead and is upstream, the overtaking car still experiences a slight drag reduction of about 5 counts. So for those automotive manufacturers that are a little more desperate to reduce the drag of their car, they could always hire people to drive just ahead of you wherever you go really and drop your car by about 5 counts. That'd be pretty good. Anyway, interestingly, as the overtaking car approaches the car to be overtaken, the car to be overtaken experiences a massive increase in the side force, so this graph here, and this side force is now pushing the car away. This, I guess, can be explained in that the downstream car is pushing air ahead of it, and that air is trying to get out of the way. But on one side, there is this upstream car, so it just hits its side and pushes it away a little bit. And like the drag coefficient, once the overtaking car is about level, then the side force of the car being overtaken drops dramatically, and now the 2 cars are being pulled together. There's a suction force between them. And I think this is effectively the Venturi effect, where you have both of these cars side by side, and the air that hits the front car, or the front of both cars actually, needs to go around, and much of it will get funneled between the 2 cars. That then causes the air to speed up and the pressure drops, which then makes the two cars suck together. So that's what I think is going on here with the suction force down here. And as the overtaking car pulls ahead, the side force returns to about normal. So the pressure coefficients on the armored bodies can be seen in figure 8 throughout the overtaking maneuver. Let me zoom out a little bit now. So figure 8 here. Actually, I probably should zoom in now. Okay, here we go. So, and what we were talking about with the side force can kind of be seen in the middle images where the armored body upstream experiences a low pressure coefficient around where the downstream armored body is, and the surface just upstream experiences a high pressure coefficient. So you can see here, as this one pulls close, this pressure drops while upstream it's a bit higher. So that's, I think, the flow's hitting this first one, coming around, hitting the second one, and then has to go through the middle here and drop in velocity. And interestingly, in the bottom two figures of images of this figure, as the downstream car pulls up to the upstream car experiences a massive drop in the pressure coefficient just behind the leading edge. So this blue region here is a massive reduction compared to when the downstream car is much further downstream. That would probably affect the lift of this upstream car too, I think. I mean, I can't see the underbody, so I don't know if it is affected or not. But if we look at figure 9a, we see the effect on the lift. And now, while these graphs promise to be very useful, they unfortunately aren't as useful as what we might hope, because the x-axis is in time, and I don't have a complete idea as to what the time steps refer to in the overtaking maneuver. I think that 0.5 seconds is when both cars are side by side, but I'm not 100% sure here. But anyway, we can see that throughout the overtaking maneuver, the lift dramatically increases, so we get this spike here. And now from these values, from the CFD, we need to take it with a grain of salt, but generally speaking, the lift of the car being overtaken about doubles. And that agrees with my preliminary analysis of the pressure coefficients in figure 8 here. So maybe the underbody isn't affected as much, or maybe there is a higher pressure under there. That's something for further investigation. Now, in figure 9c, we see the pitching moment of the upstream car, and while it's being overtaken. And this is pretty funny because it's trying to nose down. So as you overtake one car, the car you're overtaking wants to pitch down in terms of its nose. I wonder if your car would want to pitch up. I'm not too sure. They don't put this information here, but that's quite interesting. So that could definitely mess the car stability up. Now in figure 14, if I scroll down to figure 14 here, we see the fluid structure interaction in this car. So that's the investigation part of this paper. And they show just how much the different panels around the upstream car wanted to form based on the different frequency modes. And the amount of the deflection of these panels are in orders of millimeters and hundreds of micrometers. So almost nothing really, not even a centimeter. And that means that the shape of the car is pretty much fixed throughout this overtaking maneuver. And I don't know exactly if they got the stiffness on the panels to be the exact same as regular cars, but even if the panel is flexed by a couple millimeters, that's not that much for 100 km/h speed. So these panels are pretty much fixed. And with that, we come to the end of this podcast. It was very interesting seeing just how much the drag coefficient was affected and how much the side force there was, and how that changed depending on where the overtaking car was relative to the car being overtaken. And at one point, the overtaking car was being pulled into the other one, so there's this suction force. So if you like this podcast, hit the like and subscribe button. And if you want to learn how to do OpenFOAM, check out the link below. And if you are doing experiments, did you know that you have probably a 2 to 4% error in your data and you don't even know about it? In the Atmosphere Hawk link below, we go through why, the math of it, and how to fix it. So with that, we are done, and we'll see you next one. Peace, amigos.